All right, happy Thursday again. So we've got priority queues to look at today. Right, I think that's the last topic for this week. So we spent all Tuesday on the project and next project. So we got to talk about priority queues. These are lots of fun. It's just a special way of storing data here. So we fire up PyCharm. And to do this, we're actually going to take advantage of our binary tree class. So the typical way that we store information in priority queues is in something known as a heap. And a heap is a special sort of binary tree. So I think I've got that one in here, right? I think that's my recents. Our trees. Yep, so we had trees here. So we had a positional binary tree. So as far as we got, right? So we didn't work on the list-based binary tree. I think that was going to be the last piece here. So with our positional binary tree, we still had the links here, right? Where you could say, okay, what is your left child, what is your right child, and who's your parent, right? Using all of the node, this inner node class that we had. So that inner node class, right, kept links to the parent, kept links to the left, kept links to the right. So we could kind of navigate this tree structure. And we always had 0, 1, or 2 children. Let me try Word. Word froze on me last time. We'll see how well this does. So what a heap is it's going to be a special kind of binary tree in that we will always have children at every level filling up. So in a, it's a complete binary tree. If all of the levels are completely full, we would say this is complete. That's one term we would give our trees here. If you're missing a child here, you could be full in that every level except the last is complete. And then the last level, all of the children are as far left as possible. So like essentially in order, right? So this would not be full because we're missing a child here, right? So we've got to be in order. This would be full. Here, where every level except the last is complete, and then every child is as far left as possible. So it's just a simple way for us to store these things. And then I think we left off last week looking at if we wanted to store these things without using links, without having to know here's the left child, here's the right child, here's your parent, where you have to store 3 memory addresses for every piece of data you want to store, which is a little bit memory inefficient. We could actually store this in an array or a list. We could say, okay, I know the first item, right, 2 to the 0, is the first level. And then I know the next 2 to the 1 items are the next level. Right? So if we had 1, 2, 3, 4, 5, 6, and 7. Right? So that'd be a 1 here. 1, 2, 3, 4, 5, 6, and 7. So the next 2 to the 1, right, are the second level, and then 2 to the 2 is the next 4, right, or the next level here. So we said, okay, if we look at these index values, then I can do quick arithmetic to calculate the parent or to calculate the children. Oh man. So to calculate the parent, we said we were going to take your index and round it down. Or I'm sorry, divide it in half, round it down. So at index 1 and 2, when we divide by 2, no, sorry, it was index minus 1. This is why I need to cheat out of the book. So our index minus 1, then divided by 2. So I'd get 0 over 2 is 2, right, if we build out a little table. This is for our index. This is for the parent index. So at 0, there is no parent, because we're already 0. We know that one. But at index 1, we get 1 minus 1 divided by 2. At index 2, we get 2 minus 1 divided by 2. It should give me 0 and 0. And then for 4, 5, 6, and 7, if we kept going with that formula, we'd have 4 minus 1 is 3, divided by 2 would give me 1. Is the parent of index 4, oh, I'm sorry, I missed 3. Sorry, 3, 4. I was doing values. 3, 4, 5, 6. We'll get there. Yeah.
So the 4 minus 1, and then that's going to be over 2. So it's like
yeah.
after you do that for the fraction.
Yeah. So subtract first and then divide by 2.
Yeah, that's giving the parent number.
Yep, so 3 minus 1 is 2 divided by 2, which is 1. 4 minus 1 divided by 2, rounded down, still 1. 5 minus 1, 4 divided by 2 gives me 2. And then 6 minus 1 divided by 2, 5 divided by 2, rounded down is still 2. So if I look and see what the parent index is, right? So this was index, I should put in 0, 1. We'll do the index values to make life easier. 3, 4, 5, 6. So index of 1 for 3 and 4. That's the parent index. For 5 and 6, the index was 2 for the parent one. And this will work all the way through the tree. So then to find your children, we do the opposite. So if you wanted to find the child of a particular index, you're going to take your value and we just need to reverse. So we need to reverse it. And then we're going to add 1 or 2 for the left or the right, I think is what it was. So your index times 2. So we had a left child. That's not an L at all. I really got to bring my tablet. I'm sorry. I keep forgetting. The left child, the right child. So if we have our index, the left child and the right child. So at index 0, we know our left child will be index 1, the right child will be index 2. So if we take our index and double it, right, so if we do times 2, and then this is plus 1, and this is plus 2. So at index 1, our left child should be us doubled, plus 1. So doubled is 2, plus 1 should be 3. Index 1 doubled is 2, plus 2 is 4. My right child is 4. That holds out. So for index 2, me doubled is 4, plus 1 is 5 for the left child, plus 2, 6 for the right child.
So is it like the binary trees that can only be 2 child?
Yes, so specifically a binary tree that we're going to use for this, because I know exactly how many items are at each level. If it's an N tree, there's no way I can sort in a list efficiently. Yeah, I wouldn't be able to do this sort of arithmetic. So we'd have to go back to using our references, using the pointers like a link, which can work, but if it's specifically a binary tree, this will save on memory usage. This will be a more memory efficient tree because I don't need to store the reference to my parent, I don't need to store the reference to my child, and I don't need to store the reference to the other child. So all of this fun arithmetic essentially can take the place of all of these links where we said, okay, well, give me the left child or give me the right child, right? If I have a left child, if I have a right child, all this sort of work here. It's a little bit tedious, we don't need to do, right? Which is really cool. So I'm going to build out, let's make a new project here. And this is week, how did I have, 7 was trees, wow. So we're all the way to 10 now because we had some breaks here. So we'll do week 10 for priority queue. Week 10, priority queue. So if we're going to keep this structure here, which a priority queue keeps the full structure, which is super handy, we can take advantage of that basic arithmetic. I'm going to write my class for priority queue. We'll have init for our number of items is 0, and then we need some sort of storage array. So our data array, right, will be a list. And we might want to pre-size this to a certain size. We might, or we could just add stuff as we go, right?
So sometimes we're like, when we do self.data equals data, sometimes we'll make like a list like that, right?
So when we were doing like, if you passed in values, we might take the data that was passed in. For this one, we're just going to start empty. Because when we're a priority queue, things will be in a very specific order. So I can't just take a bunch of values from you without having to go put them in that order myself. So there's ways we can do it. And one of the optimizations the book gets into that we're just going to skip because it's not worth our time is if you know how many items are going into your priority queue, you can actually build it from the bottom up instead of the top down, and it's faster. Because some smart person is like, hey, this math works out faster. And everyone's like, oh, that's cool. We're just not going to bother. That's just a fun thought exercise. Yeah, so if we start empty, it's actually really easy. And really, our number of items at this point, if we're going to be in this full complete form, will just be the number of items in the list, because I'm not going to leave extra space. So I don't even need to track number of items separately, which is really nice. I can just store my data here. So with the priority queue, you can enqueue an item, enqueue some data, and then you can, let me get the list here. Let me just go grab We'll grab that PDF. It'll be a little easier here. It's in my downloads. Data structures. Come on, search. Really? There it is. I don't know why search is so slow, but that's fine. All right, and then we want our priority queue structure here. Make sure this is still capturing my screen. Okay, it is good. It locked up last time, which was really annoying. So you can add, you can get the minimum value, you can remove the minimum value, you can check if it's empty, you can get the length. This is pretty easy. Now, if you want, you can do this with a key value pair rather than just single values. I think that's more trouble than it's worth right now. We haven't got to that idea. So you can build your own dictionaries with a key value pair. We're not going to bother with that right now, and that's okay. So we're going to go a little simpler than what he has here. So we can add an item. We'll just call it add, I guess that's easy. So we can add an item. You can get the minimum item out here, and then you can remove the minimum item. So these are the ones we need to figure out how to do. All of this will be stored in our data. So the idea with the priority queue, now, so what makes this special is that the item with the lowest priority is going to be at the top. So this is not a typical line, this is like your emergency room. If you go into the emergency room and you have a bad cough, you're not going to be seen before the person who had a heart attack. Right? The most priority, so in our case this will be the minimum. You can also do one that's a max, just depending on how you want to sort these things. Typically when we do a default sort, you get low to high. So we're going to say low will be the first item we get back out. So with the priority queue, we're going to sort so that the lowest value is at the top of the priority queue. Because to get something out of a tree, right, we can always say, hey, it's right here. This will be the lowest item always at the top. So if we just add a bunch of numbers, we can sort them ourselves as numbers here. So let's look at what the process looks like. So to add something when we're empty, really easy. We just add one item. Just give me a number. It doesn't matter what it is. One. Okay, there's one. So the lowest item's at the top. If we want to add another item, what's another number? 3. So we're going to make the next item in the list here will be a 3. We can just append it, and then we have to go through the process of saying, is this in the right spot? Yeah. So when you add a new item, we need to see if it's, in our case, lower than its parent, we need to start swapping. So the process here is called upheaping, which is one of my favorite technical words. So you upheap. So you add an item to the end and you start upheaping it until it's in the right spot where it's no longer less than its parent. So for now, 3 is less than 1. It's perfectly fine. Nothing has to change. Let me see. I think I can zoom in a little bit here. Sorry. So let's add another number. What's another number? 2. So let's throw in 2. We're going to add it to the end of the list, which makes it the child of this one. And then we're going to say, okay, we need to upheap if you are less than your parent. We're not. So we're done. Right? Let's add another number. You can go negative if you want.
-1.
All right. So we'll add a -1. So we add it to the end of the list, and then we start upheaping. Is -1 less than its parent?
Yeah.
It is. Okay, so we need to swap. So we're going to swap 3 and -1. Oops, I didn't mean to swap the bubble too. So we'll put 3 here, we'll put -1 here. And then we repeat the process. It's recursive. This is why we did recursion before. We just keep on going until we hit the top. As long as we're not at the top, right, or we have no parent, we're good to go. So is -1 less than its parent?
Yeah.
It is, so let's swap. So we swap -1 and 1. Now we're done. It got to the top. Right, now we add another number. 7. All right, so we add it to the end here. It's the next available child. Is it less than its parent? No, we're done. All right, we add another number. 4. Is it less than its parent? No. Oh, we're done. All right, we add another number. What?
-2.
-2. Is it less than its parent? Yes, so let's swap. So we swap the 2 and the -2, and then we repeat. Is -2 less than its parent? Yes, it is. All right, let's swap. We get -2 and -1. Now we're done. We're at the top. So that's adding something. So when you add a value, you add it to the end, and you upheap it. You compare it to its parent, and you just keep on swapping as we go. To take a value off, then, what we're going to do is give you the value at the top. Right, so you're going to get the -2 back out here, and then we replace it with the last item in the list because we need to keep this full, complete form where all of our levels are full except for the last one. So I'll take the 2 out and put it back at the top. And then what I do is I down heap. So we up heap when we add to get to the right spot. When you remove, you have to replace the last one, and then you down heap it. It falls down. And to down heap, you replace with the smallest child. So I have two children that are smaller, but I need the smallest child. So in this case, it's -1. So I'm going to swap the 2 with the -1, because that's the smallest child. -1 and 2. And then I repeat, is 2 is 2 more than its children? Right? Should it fall further down? Should it fall down lower in the heap? No, it's not. It's done. So they're not in a sorted order, right? Because I've got 7 over here, and I've got 2 and 4 over here. So it's not sorted if I were to go in a specific order here, but it follows the form that you are never less than your parent. And this one can have duplicates. You could have another 2 over here, and that's perfectly fine. It's not less than its parent. There's no swapping that needs to happen, right? That's okay. If we wanted to add another 2 then, right, we could put a 2 over here and say, okay, 2 is less than 3. We need to swap 2 and 3. 2 and 3. But that's it. It's not less than 1, and we're done. Right? We just keep on going. So you can have a bunch of duplicates in here, so you don't need unique values, which is nice. So it gets a little tricky with the key value pairs, right? Because we might have duplicate values, and that gets a little bit awkward. So you don't need to restrict to that if you don't want to. So when you add an item, we're just going to take self.data, and we're going to append the data. Now we've added it. Now we need to start the upheaping process. So we're going to make a function here for upheap, given an index. So you tell it what index you're going to start upheaping at. So then I'll call self.upheap, and I'm going to upheap at the length of self.data -1. Right? That's the last index. How's it going? Right? So this is the index that that new item is at.
So why do you say length of the data, not just data?
So because when we want the index value, so this will be the numeric length. Then I can subtract 1 from to get the index value. So right now I have 1, 2, 3, 4, 5, 6, 7, 8 items. So my length would be 8. But the last index here is actually going to be index 7 in that storage, in the array storage, the list storage. That way I get the index out. And then we need to be able to calculate a get parent index, given an index. Right, so we said the parent index is going to be your value, so we're going to return index -1 divided by 2, forcing the order of operations here. Right? And then you could define a get left child index, given an index. We said that was going to be index times 2 plus 1. Now, you could put the parentheses here, the redundant, but I like having them here just to know that that's supposed to happen first and not rely on order of operations. I'm a little funny sometimes. So you could get a right child index, given an index. We said that was going to be the index times 2 plus 2. Right? So to upheap then, I need to compare myself with my parent. So I can say, hey, if the self.data at the index is less than the self.data at the self.getParent index of the index. Self.data, square braces there, sorry. Square braces. Index of the getParent index of the index. So compare yourself with the parent. If you're less than your parent, we need to swap. So we'll say temp is self.data at the index, and then self.data at the index will equal self.data at the parent index, and then self.data at the parent index will be the temp. Right? We'll just swap them out, and then we need to recurse. So we'll call self.upheap of self.getParent index of the index. So I guess this is a little silly to have that function 3 times, so we probably should have a parent index value, and I can just use this instead. I don't need to call this function 3 different times, right? I can call it 1 time and get the value and save it. Man, we did it 4 times here, right? 4 times? Oof. Is that all the swaps there?
Can you just go over the code briefly again?
So we're going to get our parent index, and then we're going to compare ourselves. Are we less than our parent? If we're less, we need to upheap. If we're not less, we're done. Nothing else has to happen. But if we are less, we're going to swap. So store myself, replace myself with my parent, replace my parent with myself, and then recurse. Call it again, starting at where my new position, right? I'm going to recurse starting at the parent index that I just put myself in. and I can keep on going. So that will do this bubbling up, the upheaping. So if I put a really low number in, it's got to go all the way to the top. Now, if we think about performance of this, right, when we talked about trees, right, they had that really cool power of 2 property. So we looked at, hey, if you are a binary tree, at most you'll have, it's a logarithmic scale of how many items fit at each level. Now, technically a binary tree that's 1, 2, 3, 4, like that only ever has right children, is still a binary tree, it's just a terrible one. We couldn't really do anything about that until you get to 350, you learn how to balance them. But this heap structure, we're forcing it to be in this complete form. So it will always be in the form based in the power of 2. So at most then, the performance of this is going to be O of log n. Right? If we keep ourselves in this, every level has the next power of 2, next power of 2, the most operations we're going to have to do is based in the power of 2, which is logarithmic scale. So if I've got 16 items, right, I only have, is that 4 levels? Or 15 items is 4 levels? If I've got 32 items or 31 items, I have 5 levels, and on and on and on, because it's all, each level has the next doubles, double and double and double. So performance-wise, this actually is relatively quick. A logarithmic of n performance is pretty good. Much better than the linear performance in n, right? So upheaping is pretty quick. So to add something, we go add and we upheap. So this is, because upheap is O of n, this will be O of n, or log n here. Right? To tell you what the minimum value is, we're just going to return self.data at 0. We know what that is, so this is a constant time operation, because it's always the top of the heap. Now, if we're empty, we should probably fail, but this will just crash anyway if there's no value there. So that's probably okay. We could come up with a custom error if we wanted. Could do custom error if we wanted. But if it's an empty list and you try and get index 0, Python's going to yell at you anyway, so that's fine. So to remove the minimum then, that was the next one here, we need to get the value. So we're going to have the temp value is going to be self-data of the first value. Right? That'll be the min value. We're going to give that back at the end once we're finally done, but we can't return yet because we need to fix our structure. So we're going to take our self-data at 0 and we're going to put in self-data at the length of self.data. Oh, I'm sorry, you can just pop it off, sorry. So self.data.pop. Take the last item off. Right? This removes it from my list, puts it in this location. So now I've taken care of that. I don't even have to do anything special to remove, right? There's no links that I have to change. I don't have to say, hey, parent, you no longer have a right child or a left child or any of that nonsense we had to do with the links here. We just take it out of the list, put it here. Everything else is done for us. That's why the list-based way of storing trees is so nice and easy, because all that work happens for us. Then what we're going to do is we're going to call self.downheap, starting at 0. So we need to make a downheap function. Downheap will start at the top and it will fall down until it's no longer greater than its parent. So when you upheap, you rise up until you're no longer less than your parent. When you downheap, you fall until you're no longer greater than your parent. So this is our downheap, given an index. So we need so the problem with the downheap now, this one is a little bit trickier because you need to replace yourself with your smallest child. But we don't know if you have children, right? Depending on what level you're at, we have to see, do you even have a child or not? So the arithmetic will always be the same, but we need to compare ourselves to how many values we have here. So we could add in our own length as well if we wanted. So we could define length of ourself is going to be length of the self-data, right? So when I have 5 items, I have 5 items on my list. When I have 7 items, I have 7 items on the list. This one's really easy, but now I can compare the length of myself. So when we start downheaping, we need to say, if we have any children. If we don't have any children, there's no work to do. Excuse me. So if self.get the left child index of my index is, so if the index exists, it has to be less than the length of self. Right? The length of myself will be the length of my data. This just saves me typing 2 extra keystrokes, right? So if the length of self is greater than the left child index, then I know I have a left child index. If it equals, I don't have an index there, right? Because I'll have 7 items, but I don't have index 7, right? So it has to be less than for it to exist. So if I have a left child, now I can start my downheaping process. If I don't, I'm done, right? The else is, we finished. There's no more children you can't be less than your children. You can't be bigger than your children. Right. So this is moves down the heap until it's no longer greater than its children. For this, and then the upheaping was moves up the heap until it's no longer less than its parent. Okay? So if we have a left child, now we need to see which child is the smallest child, because I need to swap with my smallest child. So I know I have at least a left, so I can check, do I have a right? So, or we can say, hey, my smallest child index will start off as my left child index. And if we're doing this twice, I guess we'll just say left child index. So I'm going to start it off as the left child index until I know otherwise. So that's the smallest. And then if my right child index, so I'll have a right child index, will equal self.get right child index of my index. And if the right child index is less than the length of self, I have a right child. If I have a right child, let's see which child is smaller. So if the self.data at the right child index is less than the self.data at the left child index, then my smallest child index becomes the right child index. So if I have a left child, I'm going to assume that's the smallest. If I also have a right child, now I'm going to compare, is the right child less than the left child? If the right child is less than the left child, my right child is my smallest child. If it's not, my smallest child is still the left child. So this just saves a bunch of else cases here with just these here. So really we could kind of combine these here, right? If the length is less and my child is smaller, right? Then I have a new smallest child index. Then what I'm going to do is I'm going to swap, right? Only if I have a left child, regardless of if I have right or not here, I'm going to swap. So I'll have temp is self-data at the index, and then I'll take my self.data at the smallest child index, and then I'm going to, assign myself to the smallest child index, right? Swap with my smallest child, and then take my smallest child and put the temp value back. So that does the swapping, right? Grab myself, replace myself with my smallest child, put myself back in my smallest child spot. I've gone down in the heap here now. Then I'm going to recurse. We'll call it again. So we'll call self.downHeap given my smallest child index, right? The place I just put myself here, keep on going. Repeat the process here. And we're going to keep on going, keep on going, keep on going, keep on going, as long as I have children and I'm less than those children. No, I'm sorry. I forgot one last thing. So this is the smallest child here, my bad. Before we swap, I have to make sure I'm actually smaller than the smallest child. So I know which is the smallest child between the left and the right. Now, this is all if self.data at the index. Now, is if I am, this is if I'm greater than my self.data at the smallest child index. Then I swap. Because if I'm not greater than, I don't need to fall down any further. I shouldn't swap if I'm less than. And if we're equal, sure, it doesn't matter, right? There's no work to do if I'm equal. So if I'm greater, I need to fall down to the next level. If I'm greater, I need to fall down to the next level here. All right, so I think that ought to work here for down heaping. So to remove the min, we down heap 0. And then when we're done down heaping 0, we're going to return temp. Right? This will recurse as many times as it needs to, as falling this new value down as many levels as it has to. If I've got 1,000,000 items, it'll go through all the levels, which I think is only like, what, 14 levels to hit 1,000,000 or something like that? 13 levels? It stores really nicely here, which is awesome. All right, and then I think the last thing we wanted here, right, from the text here was is empty, whether or not we're empty or not. So we'll define is empty, and we're just going to return length of self.data, or length of self equals 0. If we have 0 items, we're empty. That one's pretty quick. Right? We can take advantage of the code we already had. So we have add, we have min, we have remove, we have is empty, we have length. Okay, so we can start adding items and do it. Again, I'm not this is a good way to build software. It's not a good way to learn software, in my opinion. So we don't bother with all this composition stuff with the items and things like that. We're just not going to bother. So we're just going to have our own. And then the unsorted priority, why would you even build a stupid one? So you can build one that is just a regular list and it's n-based. You have to go find the smallest one every time. That's fine. But you do get really fast adds, which is cool. But that one's not worth building. And if you build it in a sorted list, you get slow adds, but you get fast removes if you keep your list sorted. It turns out our heap structure is the best way to do this. So the heap structure, thanks to all this math here, right? This is, sure, it's good math. We will up heap and we will down heap. And it has the fun pictures here. Yeah, parent. Look at that. Why is it J? What, J is like the worst variable name he could come up with here. I have no idea why the author has J here. Right? That doesn't make any sense, right? Why J? It's the index. Right? He calls it J, whatever. Right? -1 divided by 2. Oh, floor divided by 2. That's right. We need to make sure we floor for parent because we definitely want indexes here. Floor divided by 2. It's good to copy it off the author sometimes here. And then if we have a right, if we have a left, sure, we can just give you the index here. Swapping. Python lets you do a swap in a single line. I've never been a fan of this, just because you can't do it in other languages, and I never got fond of typing it out in a single line. Instead of doing 3 lines of the temp, you can swap. So then upheaping, you start upheaping with your parent if you need to, right? If you are greater than. Oh, and this is if you have not reached the top. That's right, we need to stop when we get to the top. That's the last piece here. So to upheap, we will stop if we are upheaping at 0. So this is if my index does not equal 0. Or really, if you want here, if you don't like indentation, some people don't like when things are indented, we can say if index is equal to 0, we return. That stops the function without having to be this all inside of if it's not 0, keep on going. Essentially, that's all it is. Because once we get to 0, you don't have a parent, there's no place left to go. Right? This is our base case, one of the base cases in this recursive function. When you get to the top, stop. Or stop when you're no longer less than your parent. Right? You have multiple base cases here with this. So index 0 is the top and has no parent. Again, just a different way of going about it here. So if he throws it all in this one here, fine, whatever you want to do here. Right? Small child, check compared to the right child, find out what your small child is. If you're less than, swap. He adds the swap function, sure, that's fine. I guess I feel bad about having the same code twice with this temp stuff here. I could combine that and not have it twice. But that's fine. I don't feel too bad about that one for swapping. So init, length, add, min, remove. Awesome. So then timing wise then, O of 1, log n and log n for remove and add. And again, it is amortized, right? The average here, because eventually we have to resize the underlying list. So every so often it's n operations, because the list beneath has to resize. But on average, right, we get to average that cost out, it's still log n here, which is great. And this is the bottom up. So if you know how big it's going to be, right, it's n log n, but you can do it technically faster if you build it from the bottom up. We're not going to bother. That's just a fun thought exercise here. But you can build it out if you want here as you go. If you want a priority queue, you can use the heap queue. It has one built in for you. You don't have to write your own. But it's a fun exercise to write our own and to go through that process of doing it here. So you can heap push, you can heap pop, heap push pop. Put an element on pop and return the smallest item? Sure. So it's more efficient to do it once at a time because the size of your list never changes. So if you're adding, like, sure, that's someone really smart realized we can combine these and save some time here. Replace, sure. Heapify, this one I like here. You can turn a list into a heap, sure. The n largest number of items, which is fun, or the n smallest number of items, that's fun. And then if you want to use a priority queue, you can use it to sort something in a sorted order by throwing everything in the queue and then pulling them all back out. So putting n items into a priority queue takes n log n operations. Pulling them back out takes n operations. So it's really like 2n log n, but remember we throw away our coefficients because of funny math like that. So you can sort something in n log n using a priority queue. We haven't got to the other sorts yet. We'll get to the other sorts as we go. We do that week 13. We'll talk about other sorting operations. The other ways we sort are usually kind of slow, right? So n log n is not too bad for sorting using a priority queue. That's kind of fun. Yeah, oh, here's the other, why do they talk about the other sorts here? We'll get to those later, right? You can do other sorts, or you can use the heap sort. Adaptable priority queues are fun. So this one lets you use the location. Again, we're not going to get into this. This is more advanced than we need to get into for this one here. But you could like pull someone out of the middle, which is really what happens like in the emergency room. People can just walk out. You're just gone. Sure, that's fine. Yeah, I think that's it for the chapter then. This one's kind of fun. It's a specialty data structure. It's good for things where you have a priority for things, right? If it's important to keep it in this sorted form where you will always want the smallest or always want the largest on the top, you can use this, and the entire thing doesn't need to be sorted, right? Because it will sort itself as you pull out the items here. You can pull them out this way. So if you think of like when you go to Cedar Point and do the rides there, they've got the regular line you can get into, which is a regular queue, and then they have the fast pass. If you want to pay money, they'll let you get on rides faster. The fast pass sort of turns into a priority queue with the regular queue. Right? They'll take a couple of people from the fast pass line, they'll take a couple of people from the regular line and merge them in. And it usually works out because less people pay money for the fast pass. If everyone bought a fast pass, you just have a regular queue again. You wouldn't have any priority. So they rely on people not wanting to spend extra money to make the whole system work, which is fun. Yeah, so that's our priority queue. Next week, we're going to get into maps. We can build our own map or build our own dictionary. Right? Here's the key and its associated value. We'll look at how we get to build our own. And it turns out using a hash table is actually really super fast, which is really fun. So we'll look at why we can do this really fast with a hash table. We're actually going to skip lists. It's in the chapter, but we're just not going to bother with it. So don't worry about it. We don't even need to talk about it. And then we get into search tree. So a binary search tree is in a very specific form to keep it in a sorted order. And then we'll talk about sorting and selection. And we'll talk about ethics. And then we've got the last week reserved for working on the final project. And then instead of a final exam, we'll meet at 3 p.m. and go over our group projects. Right? Again, we do need to pair up for this one, right? Because one of the assessment items here that we learn how to do is to work as part of a team. If your teammate does nothing for you and just doesn't reply, doesn't respond, I'm not going to penalize you for it. But you've got to like tell me that you've been trying to reach out to them. It should not be a surprise to you if you're a terrible teammate. Please don't let that happen. Right? It's terrible in the workplace. It's terrible in school. If someone is not doing the things they're supposed to do as part of the team, they need to be told. Like, don't wait for them to be like, oh, they're probably going to realize they haven't turned a bunch of stuff in, and maybe they'll get to it later. Like, you just got to be upfront and direct with people. Like, hey, you said you were going to get this done. You didn't get it done. If you don't end up getting it done here, you're not going to get the score on the final project. And remember, the final project makes up 40% of your score. If you don't get a score on the final project because you didn't do any of the work, you cannot pass the class. Like, mathematically impossible. That's on purpose. Right? This final project is a must. So, and again, we're just doing pairs, maybe a trio, depending on how the numbers work out here. But with pairs, it's not so bad, and you can pick yourself. Right? I'm not going to put you into groups, so you go find a classmate to work with. And usually it works out pretty well. If two groups both lose a partner, and we still have a little bit of time left, I'll see if they want to work together with a partner who actually wants to work. But we're going to talk about this one after the last project's due. So our last project was going to be due March 26th. So if we talk about the final project on March 26th, we have basically a month, right? So March 26th, we've got week 13, week 14, week 15, and then the week after. If you can get it done early, that's fantastic. I would love for you to be able to have it done and working by 4/18, so you don't have to worry about this for final exams. You can actually focus on your other final exams like last time. If you can get it done early, great. If you want to take all the way to 4/23, 3 p.m., go for it. Right? As long as it's done by the time you present, I'm happy. But ideally, we can get it done and knocked out early. Okay? All right, thoughts, questions, concerns? Feeling pretty good? We're in the later half of the semester now. So we'll do hash tables and maps. We'll do search trees, but only the basic level. We don't do all of chapter 11. We don't do all of chapter 12. We're going to, at this point now, we're getting into, here's topics we'll intro, you're going to go deeper in 350 level, kind of like we did in 1501. Once we got through the core stuff, here's a couple things we're going to get into deeper next class, but let's scratch the surface. So we're going to do that same sort of idea here. So we won't go crazy deep with hash tables, we'll go enough. We won't go crazy deep with search trees, we won't go crazy deep with sorting and selection. Right? We're just going to start the topic. So in terms of reading wise, we're mostly skimming here. We're taking the couple pieces we're doing, just skim the rest, know it's there, you can get back to it later. And again, I'm pretty sure they still use this book for 350. I got to double check on that for you. I keep forgetting to ask. Oh, my eye's bothering me again. But that's the plan for the rest of the semester. Sound good? All right, fantastic. You folks take care. Let me know if I can do anything for you.